Hi, good morning, everyone. Welcome to our Trials at ICES workshop for the 2022 forum. My name is Mike Patterson, and I'm going to help moderate the session today. We have a terrific list of speakers on tap for today's session. We hope it will be informative and hopefully stimulate some discussion. So I'm just going to quickly run through a few quick overview of the speakers and a few reminders. So the session will begin with an initial introduction by Dr. Stephanie Dixon, and then we'll follow by a series of 5 presentations by our ICES scientists, trialists. Stephanie will talk about the organ donation trial Register Now, which is a stepped wedge cluster randomized trial, followed by Dr. Amit Garg, who will talk about a series of dialysis center clusterized randomized trials, and in particular the MyTemp trial. Followed by Dr. Doug Lee, who will talk about several pragmatic trials in the cardiovascular disease space being undertaken at ICES. Followed by Dr. Merrick Zwarenstein, and Merrick will describe his Ontario Printed Educational Message OPM trial and several other pragmatic trials related to this. And then finally, we have Dr. Noah Ivers, and he will highlight several of what he refers to as implementation trials that are currently underway and some of the challenges in those. That will be followed by what we hope will be at least a 10-minute Q&A session, which will take us to 10:45. Just a couple of quick reminders. Those of you online, if you could please mute yourself and keep your video turned off. If you have questions for the panel, if you could please enter those into the chat function, and I will monitor those, and hopefully we'll have enough time to get to as many of those questions as possible at the end of our session. And then finally, bios. You will have seen hopefully that bios for all of our presenters today, are available on the participant platform under the sessions. You can also find more on our speakers on the ICES web as well, and you can, there's a direct link to the ICES website on the platform as well. So I guess that's all for me at the moment. Enjoy the session today, and I'll turn it over to Stephanie, who will kick things off.
Great, thanks, Mike. So today we're going to talk about the trials at ICES, and a lot of this work comes from the ICES Trials Working Group that was formed in 2019, where we looked at trials and potential limitations at ICES and presented a report to the Scientific Advisory Committee. So before we get into, some pieces about actual routinely, how we can use the routinely collected data, we might want to consider why we would use randomized trials. And so some concepts that you are likely aware of are the internal validity and external validity. So with internal validity, it's the extent to which we can make inferences about the treatment effect. So that is the degree to which the causal relationship is trustworthy. Whereas external validity is the extent to which we can generalize or apply the results to the population. In a large enough sample, randomized trials guarantees internal validity of our estimates, as it tends to balance the distribution of measured and unmeasured confounders between the trial groups. Internal validity is not enough on its own, but without internal validity, then external validity is meaningless. Though there are some other considerations in trials, such as blinding and recruitment, that could potentially lead to some biases that may jeopardize the internal validity. Now, with external validity, that comes from the way in which the trial is sampled and how similar it is to the population. So this means that results are generalizable to the population from which the sample is obtained, but often will be applied to other populations of interest. Randomization on its own does not imply external validity. So the history of trials at ICES, and this comes from the report that we had created for the Scientific Advisory Board, we found that to date, there's many projects that involve trials in some capacity. This could link trial cohorts for long-term follow-up or additional outcomes. This could be used in trial planning and other ways which we'll explore in a few minutes. These trials tend to be pragmatic in nature, which we'll get into. And they often evaluate an educational or procedural interventions, focusing on interventions that already exist in usual care. Rather than individually randomized trials, which many of us will be familiar with, they use a cluster randomization design where intact groups of individuals are randomized and they form clusters. The clusters can be quite varied in nature. So we found that some of our trials at ICES include clusters that were hospitals, primary care clinics, dialysis facilities, physician offices, cardiac centers, nursing homes, and many more. So let's get into what I mean by pragmatic trials. When we think of trials, we often think of a very controlled setting in which many elements of the trial are prescribed so that we can get at the true intervention effect. These studies have been referred to as explanatory. Pragmatic trials, alternatively, are intended to inform a real-world clinical policy or program of choice. It's important to note that these two approaches are not a dichotomy, but rather a continuum. And in fact, there's 9 different domains that can have varying level of pragmatism for your trial. So it's important to ensure that your trial design fits the purpose of study. So this is the Pressy 2 wheel, and I recommend if you're interested in learning more about pragmatism to explore it further. So in an individually randomized trial, as we talked, if we think of a 2-arm trial with sufficient number of individuals, we would expect that we could equalize the distribution of measured and unmeasured confounders across 2 arms to understand the treatment effect. In our observational research, we would tend to use other methods to try and equalize the group, such as propensity scores. So here we have 23 individuals, and we would randomize them to one of 2 arms. And what's important to note here is that we would have 23 randomization units. Another design that randomizes the intact groups, so that cluster randomization trial. Here we have individuals who are grouped together in some practical or meaningful way. So individuals in a hospital or individuals who have a fondness for clipboards or green shirts. Here we can think that individuals who are in a group tend to be more similar than individuals across groups, and that these individuals within the group are correlated. So as with our individual design, we would randomize individuals. Now we're randomizing the clusters themselves. We can see here that we have the same number of individuals in our earlier example. So we have 23 individuals, but now our randomization unit is 7. These trials tend to align with the pragmatic agenda with broad eligibility criteria. They fit in a usual care setting and offer flexibility in the delivery of the intervention. But cluster randomization has some considerations that we need to think of. First, we need to be able to justify why we're using a cluster level randomization. This is a natural choice when we have a cluster level intervention. Other levels could be a professional level or individual level. And when they aren't at the cluster level, you need to justify why you're using this design. Some have justified using treatment contamination, administrative ease, or for ethical reasons. Now, contamination is a tricky one because it's likely to be reduced when you randomize at a higher level. But the problem of contamination can often be overcome by increasing your sample size. So in terms of current guidelines, they say that cluster trials are only more efficient when contamination is expected to exceed 30%. A big consideration for cluster trials is that they're less statistically efficient compared to individually randomized trials. And they're also more methodologically complex. So what do I mean by that? Well, our level of randomization does not always align with our level of inference. We are at risk of having increased type 2 error in our sample size, which can lead to underpowered tests, and increased type 1 error in our analysis, which could lead to an underestimation of the variance or standard error, resulting in spurious statistical significance and narrow confidence intervals than nominal. So we need to consider ways to improve efficiency through our different cluster designs. So randomizing at the cluster level does have a cost associated with it, and that cost is the statistical efficiency is reduced. This is reduced as a function of the correlation in cluster size. If you think about the earlier example, both designs had 23 individuals, but the first had 23 randomization units, whereas the second had 7 randomization units. So even with the same number of individuals, the power will be different based on the design choice. So we need to consider the effective sample size. And there's implications here because of this reduction in statistical efficiency. What's commonly understood is the need to inflate our variance due to clustering. Individuals are more alike, and so they reduce the variance, and we have to inflate it. A less commonly considered issue is that because the number of randomization units are reduced and often small in these types of trials, we need to make some sort of small sample correction in our analysis. Most of the methods have been developed and applied to trials rely on the law of large numbers. There's also the consideration of variable cluster sizes, which we will get into a little bit later. So the key characteristics, we have correlation. This means we need a larger sample size and our precision is reduced. So what are some of the ways to improve efficiency? Well, we can use different types of restricted randomization. In the example that Dr. Garg is going to provide, we used covariate constrained randomization. A little note there, we should always be using a design-based analysis where the covariates that you constrained on need to be included in your analysis. You can use matching or stratified designs, which was used in one of our trials, the enhancing access to kidney transplantation. You could use a cluster crossover design, which I'll touch on briefly. And you could use a stepped wedge design, which Dr. Lee and I will mention in our examples. So now let's get into randomized trials at ICES and how our routinely collected data can be used. This January, the report from our working group was used to create a website on the ICES intranet. We have included a number of resources and included information on pragmatic trials, cluster randomization, some of the examples you'll see here today, and ways data can be used. We have resources, so we have links to the living textbook from the NIH Pragmatic Trials Collaboratory, as well as a website from Queen Mary University featuring a number of resources for cluster designs. We also provide some ethical considerations, though I must say that this is a very complex issue and needs to be carefully considered for each trial independently. We provide some additional context as well. And I want to say a special thanks to Aaron McDonald, Hadass Fisher, and the communications team for getting this website up and running. So how can we use routinely collected data during our trial development? So one of the best pieces of advice whenever someone's interested in doing a trial with routinely collected data is to do the observational research before embarking on a trial. This will give you an understanding of your current practice, make sure your results align with what you see, and also from our research, make sure that you have the appropriate validated codes or use details from the concept dictionary is always recommended. With trials, it's important to have appropriate estimates for the parameters needed in our power calculations. I'll come back to this in a moment. It's also important to understand the cluster composition and movement. As an example, individuals receiving dialysis naturally cluster within a dialysis center, making these centers appropriate units of randomization for certain interventions. We've found that in some cases, there's a lot of transfers between more than one center, where centers may be acting as an overflow center. So this information is important at the randomization or in the planning stages because it may make more sense for some centers to be randomized as a single randomization unit as opposed to separately. So now let's get back into that power calculations. I want to talk about the FLUID trial. FLUID is a pragmatic cluster randomization trial where hospitals are the unit of randomization. This study was conducted through ICES Ottawa, and the example comes from Dr. Monica Talliard. I have to say, Dr. Talliard is a superhero in the area of cluster randomization trial, cluster crossover, stepped wedge design. So if you're interested in any of these approaches, I would definitely look at some of her publications. In short, this trial looked at comparing two fluids in the hospital, normal saline or Ringer's lactate, on a number of outcomes. At the beginning of the study, half the hospitals were randomized to one arm versus the other, and then they crossed over to the opposite arm partway through the study. ICES data is used in both the design and analysis. So why is this so interesting? Okay, so with cluster crossover, not only do we need to have an estimate of the hospital correlation, but we also need to have an estimate of the period effect due to the fact that the hospitals cross over and experience the intervention at different times. One of the main difficulties in designing these studies is having an appropriate estimate. Our options are to use commonly used rules of thumb or estimates from proxy outcomes. So when we use commonly used rules of thumb from the literature, when planning the study, we would require 46 hospitals to be randomized. Now, using ICES routinely collected data, we would only need to have 6 hospitals. So what's the take-home message here? Well, there is a value added by making use of routinely collected data when planning our study. So we would then potentially prevent creating a needlessly large trial and preserve some of our resources by limiting the number of individuals or randomization units used in the research or experiment. However, sometimes routinely collected data is not available, so it's also important to publish any estimates for your parameters, particularly correlation parameters, in your protocol and your final analysis. I also want to touch on that trial data. So some considerations when you're thinking about using routinely collected data is whether or not your ICES has the data that you need to properly analyze your trial. So in some circumstances, you may need to collect additional data. Another consideration there is whether or not that data needs to be linked to ICES so that it can be linked to other databases, or if it can stand alone and be analyzed on outside of the ICES network. You may want to think about whether or not your trial involves multiple jurisdictions. There's different policy, privacy requirements and legislation across provinces that do not necessarily allow for sharing administrative data at the individual level. You need to consider how this might impact your trial, and there's some potential solutions where individual analyses can be conducted while adhering to privacy policies that we're exploring that may be also preferable over a cluster level or meta-analyses. The Health Data Research Network Canada has some useful resources for both observational and trial work across multiple provinces. So routinely collected data can also be used for trial implementation. As mentioned, one way to improve efficiency of the design is to use a form of restricted randomization. And this was done in the MyTemp trial, where we used covariate constrained randomization. We have also used routinely collected data during a trial for interim reports presented at data safety monitoring boards. We've done this for an Australian trial called Resolve, where this trial is being run across multiple countries that Ontario is part of. We also can use routinely collected data for performance reports as part of the intervention. This was done in the Enhancing Access to Kidney Transplantation and Living Donation, the ENACT trial, a quality improvement intervention that was embedded into and delivered into routine care. So there's 4 different components, and one of which was a performance report that was delivered to the clusters to be reviewed by their leaders. They received an understanding of how their program was doing with respect to transplantation. And these reports were generated by routinely collected data at the Ontario Renal Network. Finally, some of the more obvious ways that routinely collected data can be used for the final analysis would be to assess the intervention on your pre-specified outcomes. We can look at additional outcomes, long-term follow-up, and even do some post-marketing evaluations. It's important to think through not just your main trial objectives, but any sub-studies or future work that may be of interest so that this can be incorporated into your planning. For existing trials that want long-term follow-up or to link their cohort for additional outcomes, potentially you need to know this in advance for the consent forms and data sharing agreements, having the correct language for linkage. So next we're going to go through some examples, and then afterwards we'll have some time for question and answers. So Dr. Garg.
Good morning. At ICES, we do many types of studies. We describe state of the union and how there are care gaps or the quality of care in certain groups. And we also do clinical prediction tools where we try to predict what the natural history will be. But let's talk about using ICES data for interventions. That is, we're changing the natural history of what would occur otherwise to make the population and patients healthier. And that's possibly the biggest impact we can have. And unfortunately, over 75% of the interventions we use in care today do not have reliable estimates of effect. Our best estimates of treatment effect come from large, multi-center randomized controlled trials. But we all know there are many challenges to doing such trials. There's issues with the time and variability across REB approvals, although that's getting better. You need research coordinators to recruit, retain, and do all the readings and manage all the data. You have limited involvement in non-academic sites. Only certain types of patients enroll in traditional trials, and that's shown very clearly. And if you think about the sticker price, at $4,000 a patient per trial, if you have a 600-patient trial, that's $2.4 million that you have to garner, often only to study a surrogate outcome with adequate power. So is there a better way, or in the words of a famous Canadian, can we go where the puck may be and not where it has been? And so I'd like to introduce the concept of S5 trials. These are streamlined trials testing solutions which are simple, scalable, and sustainable. And streamlined meaning large pragmatic randomized trials for certain types of interventions that are low risk, where we use an efficient approach to patient consent, where the solution is delivered in routine care without coordinators, and we leverage existing data for almost all the trial needs. And could this be a better trial done more quickly at a lower cost? And to illustrate this, I'm going to present this MyTEP trial. So I'm a nephrologist, and when we provide dialysis, we set the temperature on the machine. And although there are a few ways to do this, by convention, it's typically 36.5 we set the temperature at. But there is an alternative. We could measure a person's temperature, body temperature at the beginning of the run, and then set the temperature below their body temperature. And a lower versus higher dialysate temperature may increase peripheral vascular resistance and increase cardiac output and alter vasoactive peptides. You typically drop your blood pressure about 25 to 30 millimeters of mercury during a hemodialysis session. And depending on the different definition, 10 to 40% of hemodialysis sessions have intradialytic hypotension. And in small trials, there's less a drop in blood pressure and less intradialytic hypotension with a lower versus higher dialysate temperature. In some observational studies, the interventions associated with the lower risk of all-cause mortality and cardiovascular mortality. And in one RCT, there was less cardiac and brain injury on MRI. And so we were quite excited to study this intervention because it appears to be well tolerated, it's safe, it's easy to implement in all dialysis machines worldwide, and there really is no cost to delivering the intervention other than minimal nurse training. And so this is a solution which is simple, scalable, and sustainable. And if you did prove this intervention reduces the risk of serious outcomes that matter most to patients and providers, that would have a worldwide impact because immediately all programs worldwide would use that as the standard of care. But the question is, how can we do this trial in a streamlined way? Because as mentioned, if we wanted to look at an outcome, let's say death or cardiovascular events, and we had about 3,000 patients followed for 2 to 3 years, even if you get down the price to $3,000 a patient, you're looking at a $9 million trial. And for $4,000, it's a $12 million trial. So we proceeded to conduct this trial to answer the following question. Does a center-level protocol of personalized lower temperature dialysate versus standard temperature dialysate reduce the rate of cardiovascular-related deaths or hospital admissions? And we call this the MyTemp trial. For reference, here's the peer-reviewed publications on patient partnership in the trial, intervention implementation, the pre-specified protocol, and the pre-specified statistical analysis plan. And we involved 84 hemodialysis centers in Ontario. These are the black dots. They care for about 8,000 patients at any given time. It's about 90 patients per center. We randomly allocated these centers into the two groups. The trial period was April to March 2021. April 2017 is a 4-year period. All patients, when they initiated dialysis, were followed for a maximum of 4 years for death or emigration, which occurs rarely in Ontario in this population. And the primary outcome was cardiovascular-related death or hospital admission with MI, stroke, or heart failure. The research design was a highly pragmatic randomized trial, cluster-based, with another approach to consent, where all baseline and follow-up information came from ICES, and the intervention is delivered by healthcare staff. You heard earlier today about the magic of randomization, ensuring that the two groups ideally are comparable on their baseline characteristics on measured and unmeasured factors. And in this trial, we used a cluster randomization, so all current and future patients in each of these units were randomly allocated into one of the two groups. And because there's no magic about randomization when you have small samples, in this case 84, we used covariate constrained randomization to try to improve the chance of balance on baseline characteristics between the two groups. And further details are provided here. Patients were notified about MyTemp through posters, letters, and presentations to some patient and family advisory councils. The dialysis director, who was a healthcare provider, needed to provide consent for their center to participate in MyTemp. And a patient or their nephrologist could decide to opt out of the randomly allocated dialysis temperature. MyTemp met the necessary criteria for altered patient consent according to the REB. The intervention was considered to be a minimal risk to patients. Altered consent requirements would be unlikely to adversely affect patient welfare. It could be argued for a trial of 80 dialysis centers caring for 8,000 patients. It could be impractical to seek individual patient consent from a time, financial, people, and admin perspective. And all participants were notified of the trial's conduct, and anyone could opt out if they desired to do so. From my perspective, the data collection also is not intrusive because we're using ICES data. And this really does mimic what we do in routine care. We obtain consent for patients to receive dialysis, but we don't obtain consent to all the different elements of dialysis. But I fully acknowledge the ethical considerations are not black or white. And here's some of the work we've done in this area related to this trial and dialysis-based trials. 99% of the information came from ICES data. And as you know, the people who record the codes are unaware that a trial is going on in this open label trial. And we were able to analyze all ICES historic data, which was very useful to understand patient movement between centers, event rates, including competing event rates, their primary outcome, etc. The delivery of this intervention was not by research coordinators, it was by routine healthcare workers. In other words, we needed to train over 1,300 busy dialysis nurses across 42 centers to deliver personalized temperature. That's at the beginning of the trial, and there's turnover in these units, and also new nurses that came into the trial. And how you get health professionals to implement a protocol for care and change their behavior is tough. And so prior to the trial, we worked with Justin Brousseau, who's a health psychologist, and we interviewed dialysis nurses and physicians to try to understand what were the barriers and facilitators they thought would be to adopting the intervention. Again, because there's no research coordinators in the field. And so there's a framework of behavioral change, and I'll give you a flavor of this. Like, there might be belief about consequences. For example, the nurse might say, well, if I do this, my workload's going to increase. And then you can kind of tailor this to say, well, evidence suggests there's less intradialytic hypotension, which would decrease your workload and stress if that were to be true. You have to think about the environmental context and resources. Like some dialysis machines don't go down by 0.1 degree increments in temperature. It's only 0.5, so you have to adjust your protocol accordingly. Sometimes there wasn't enough thermometers in units, so we had to address that before the trial started. Or what if people use tympanic thermometers or oral thermometers? And so you have to plan for that. What if a patient was eating ice prior to going on dialysis or came out of the cold? So again, you have to have your protocol organized around and dealing with all these things. There could be a social professional role consideration. Like some nurses would say, we need a global medical directive so we can set the individualized dialysate temperature in this unit, which we did in some centers. So that allowed us to optimize the intervention and deliver it before the trial with orientation in services and communications and print materials. And we also monitored for adherence during the trial. And I'm really pleased to say that we achieved our target separation in the two groups. So on the x-axis here, you have the trial month, and on the y-axis, you have the prescribed dialysate temperature. We're aiming for a 0.5 degree difference, and we achieved that. Also, to note, once you have these trials in place, part of this period is all through COVID, and we still achieved great separation during that time. So in terms of execution, the trial period was 4 years. These 84 centers cared for about 16,000 patients, 8,000 at the beginning of the trial and 8,000 during the trial. This includes all types of patients who would receive the intervention routine care, including those with significant comorbidities. We studied about 4 million hemodialysis sessions during the trial. We achieved the target separation in the intervention between the two groups. I think if we did this again, we could do this trial probably in less than $1.5 million. It was a little bit inefficient the first time we did this, versus, again, a sticker price of $9 million. And it was done faster than it would be in any other way. And so now we're just waiting for the final data to update at ICES, and we're really excited to perform the pre-specified analysis and know the results. So to summarize, at ICES, I think we have a real opportunity to conduct S5 trials, streamlined trials, testing solutions which are simple, scalable, and sustainable. And we have the technology to do trials better, faster, and cheaper. And thank you very much.
Okay, thank you. Thanks very much. In my segment, I'm going to talk about some of the pragmatic trials in cardiovascular disease, both conducted both at and outside of ICES. Identify some of the potential advantages through these examples of pragmatic trials, and then illustrate a novel application to test the effectiveness of risk scores, as in the COACH trial. So we're all familiar with the evidence-based medicine pyramid, where randomized trials have been typically considered to be higher levels of evidence than cohort studies. Although that has changed on recent renditions of this pyramid, where in some cases cohort studies are considered as highly as randomized trials, but still randomized controlled trials are still at the high end of this pyramid. I'm not going to go into a lot of discussion about the traditional versus cluster trials, because that was really well discussed by Stephanie Dixon. But some of the disadvantages of traditional randomized controlled trials, where we randomize patients in a traditional study design, is that often many people need to be screened before identifying who can be recruited into the trial, and that has limitations in terms of generalizability. And it is hard to examine the impact of large-scale healthcare interventions or strategies using traditional randomized trials. The pragmatic trials that we've seen in cardiovascular disease have included hybrids of clinical, registry, and administrative data sources. And the unit of randomization has been at either the patient level and also clusters. And here's an example of an early pragmatic trial, the extended follow-up of the SOLVE trials for use of enalapril versus placebo. in patients with heart failure. This trial was a traditional trial which had a follow-up of about 3 years. Then using mortality and social security data, was able to link outcomes out to 12-year follow-up, and was able to show that enalapril extended median survival by 9 months compared to placebo. More recently, there have been more sophisticated designs that have used the registry-based sources, such as those in the Sweetheart registry, to study the interventions, to actually do the randomization, and to do the follow-up for outcomes for hospitalizations and vital status. And this is an example of a study of thrombus aspiration in ST elevation MI called the TASTE trial, which showed at 29 cardiac centers offering PCI, compared that with PCI and thrombus aspiration, and published in the New England Journal of Medicine. And here's another trial also done by the Sweetheart group of oxygen therapy in suspected acute myocardial infarction. Now, oxygen is something that we consider to be one of the kind of the primary, one of the traditional ways of treating patients with acute MI. This trial actually, the DETOX-2 trial, tested the intervention of oxygen supplementation in those who did not have a low oxygen status. And so oxygen was only given in this trial if they had a low oxygen saturation. And so that was compared to just giving no oxygen therapy and providing ambient air to breathe in. There was no pharmaceutical funding. It was conducted in one country, which is not typical for large pharmaceutical-based trials, at 35 hospitals, and they recruited over 6,000 patients in 2.5 years. And so it's one of the real advantages of pragmatic trials, of the ability to conduct studies in a fairly short period of time with rapid recruitment from a population. I'm going to skip over this because this was well described by Stephanie. So here's another example of some of the early work done in pragmatic trials, and this is the EFFECT trial led by the late Dr. Jack Tu, and many other scientists at ICES. And this was one of the first, if not the first, trial of public report cards to improve the quality of care for acute myocardial infarction and heart failure patients in Ontario, randomizing 86 hospital corporations to either receive early feedback on their performance versus delayed feedback, and then following them up to assess their processes of care and how they had improved. This was it was a negative trial, but one of the the trial was conducted by ICES and looked at an intervention that had not been easily tested in previous trial designs in a traditional way. At the current time, we have an ongoing trial in the cardiovascular space, is the CHOICES trial, led by Dr. Jay Udell and Michael Farku, who's a co-PI, which aims to improve lipid management in Ontario. It is a cluster randomized adaptive pragmatic registry-based clinical trial to determine if an intervention composed of a tailored multi-component strategy can improve lipid management, and it can improve statin prescribing in intermediate and high-risk patients. It's a cluster randomized design, where 14 randomizing 28 subregions, high-risk subregions in Ontario, to either intervention or control. And in the intervention arm, the physicians will get community-level lipid report cards. The patients will get educational materials. There will be a decision aid to help determine cardiovascular risk in Ontario. And then follow-up will be assessed through ICS databases, through the CanHeart cohort, and through other analytic approaches. And so in the choices trial, this is the physician report card that forms part of the intervention. It contains information on community level data, and that is then provided to the physicians using ICES data. And then benchmarks of the top performing regions in the province are also provided, again, using ICES data. And so this is provided to clinicians, to family doctors in these high-risk areas, and also contains tips for statin prescribing and the Canadian Cardiovascular Society guidelines. There was also patient educational materials that are provided on cholesterol management and lifestyle measures to improve cardiovascular health. I just want to now deviate course a little bit and talk about using pragmatic trials to assess clinical risk scores, which are specifically designed to address specific clinical problems. And this was mentioned by Dr. Garg, that this is one of the areas that ICES does well, developing risk scores and predictive models using ICES data. This is just a short list of a partial list of the risk scores that I could identify from a very quick PubMed search. Many more than this have been published, and this is an area that we do a lot at ICES. There has been a lot of with the increasing numbers of risk scores and risk algorithms. The research community has looked at the ways to assess and to evaluate these types of algorithms and risk scores. And Riley and Evans published in the Annals of Internal Medicine a kind of a taxonomy for categorizing risk scores according to the degree of validation. So level 1 is just simply derivation of a prediction rule. As you validate more narrowly, you get to level 2 and 3. And then as you validate more broadly and test the impact of your prediction rule or risk score, you get to level 5. And this level 5 includes analysis of the impact in a prospective way in different settings. But I would propose that perhaps a 6th level might be to test these decision algorithms and risk scores in a randomized trial and the pragmatic trial. And there was a recent, there have been some recent studies suggesting that risk scores should be evaluated because there could potentially be harm if it's used inappropriately. So I'll just walk you through an example of some of the work that we did in Ontario on heart failure and developing a risk score for acute heart failure to help with admission decisions in the hospital. And as Stephanie mentioned this, but I think this started by doing analyses of Ontario data and identifying care gaps. And we found that patients who are with heart failure who come to the emergency department, that some of the patients who are admitted to hospital are actually low risk patients. And conversely, some of the patients who are discharged from hospital are actually high risk. Those patients who are discharged from hospital who are high risk, some of them die after being discharged. And so this led us to wonder if there are ways that we could improve these outcomes. We know that the clinical course of heart failure is characterized by repeat hospitalizations, emergency department visits, and even mortality. Also through work using ICES data, we found that and reported that if patients who, once they leave the hospital, are followed early by either their primary care physician or cardiologist or both, there are improved outcomes. And in fact, there are a substantial proportion of individuals who do not actually get any follow-up after discharge from hospital. And so this is something that we identified could possibly be a potential component of an intervention. We, after kind of speaking with our clinical colleagues, that we felt that there was a need to develop a risk score to help physicians identify the risk of their patients. And so we developed the Emergency Heart Failure Mortality Risk Grade, or the EMERGE score. And the components of the score, its print is very small, are on the left, and that's not really important, but we're able to use this predictive algorithm to identify risk of patients as being low, intermediate, or high risk, as shown on the right. And so we were able to create a kind of a two-dimensional grid of risk, where the x-axis indicates the risk at 7 days and the y-axis indicates the risk at 30 days. And a patient can be in the red zone, which is a high risk region, or in the green zone, which is a low risk region. So we developed the score, and according to what's been published in terms of risk scores, we then validated the score prospectively in about 2,000 patients. We found that the risk score worked pretty well in stratifying risk, and also identified low risk patients who had 0% mortality at both 7 days and 30 days. We also actually compared the risk score with physicians' estimates. And so this slide shows you the risk on the increasing risk on the x-axis, and the physician's estimated risk in the purple bars. As you can see on the left side, in the lower risk deciles, physicians tended to overestimate risk. So when they looked at the patient and they put a number to that patient's risk, they tended to think that the patient would do worse than they actually would, based on the predictive model. And in the highest risk group, physicians actually thought patients would do better than they actually did. And this was kind of paradoxical, in that the highest risk group, who had the highest risk of mortality, physicians tended to underestimate risk. We think that this was a partial explanation for some of the earlier findings that we showed of physicians discharging patients from the emergency department who then had mortality after going home. When we shared these results with clinicians, they said, "Oh, this is great, but we need a trial before we implement something like this on a broader scale in the population or at our hospital." And so we launched the COACH trial, the Comparison of Outcomes and Access to Care for Heart Failure trial. It's a complex intervention of a novel strategy for acute heart failure, comprised of two main interventions. The first is using the EMERGE risk score to identify that patient's risk. So when a patient walks into the emergency department, they will have their risk estimated. They will be either one of these in a dot on this two-dimensional grid here. And then if they're high risk, the trial recommends that the patient be admitted to hospital. And if they are low risk, we recommend that the patient can be discharged directly from the emergency department. If they are low or low intermediate risk, we recommend that the patient can be admitted for a short stay, less than about 3 days or less, and then discharged early to the rapid ambulatory care clinic. So that's the second part of the intervention. This clinic, it provides all of the testing and the diagnostics and the medication interventions that would be provided in hospital, but as an outpatient basis. And so essentially what this trial is doing is identifying lower risk patients and moving their care to an ambulatory setting compared to an inpatient care setting. This is a step wedge randomized trial. And so it's the hospitals were crossed over to the intervention strategy in steps. At the end of the trial, all of the hospitals were transitioned to the intervention arm. So the advantages of this, reflecting back, the advantages of the step wedge design in this context were that all patients could be recruited. We were able to, by working through ICES, able to obtain participation without the need to obtain individual informed consent, and so had broad recruitment. It allowed us to test complex health system intervention. And one of the draws of this method was that all of the centers could ultimately develop the capacity for the clinic and to use the algorithm by the end of the trial. And that was a key selling point to the institutions. And it raises the standard of evidence, perhaps we think, a method for potentially raising the standard of evidence for risk scores and where outcomes can be assessed. So in summary, I think the just need to wrap up here, but the pragmatic trials I think will be are increasing in cardiovascular medicine. They have advantages of being real world, policy relevant, and generalizable, and could test complex interventions that could not be easily performed at the individual patient level. Thank you very much. And I will hand it over to I think it's Merrick Zwarenstein.
Oh, no, it's me again.
Oh, Stephanie, okay.
Yeah, thanks for your talk. I'm just going to get over. So I'm going to go work through an example of another stepped wedge design, but I'm going to focus on some of the methodology and considerations when trying to identify an appropriate analysis for these stepped wedge designs, particularly when we have a small number of clusters. So the motivating example comes from a Register Now trial. And this trial was developed to see if we could increase organ and tissue donation in the waiting rooms of physician offices. The current issue is that there's not enough organs to meet the needs. It's thought that the way individuals also sign up to be an organ donor through Service Ontario might not be the appropriate mechanism, since you're not really thinking about your health at that time like you do when you're visiting your primary care physician. So that might be a more appropriate venue. So the objective is to promote registration for organ donation in 6 family physician offices. This is an intervention that was developed through the Organ Donor Registration Collaborative. So it included a citizen panel, patient partners, clinicians, researchers, as well as the Trillium Gift of Life Network, part of Ontario Health, who's responsible for organ and tissue donation. So here we have the stepped wedge design that Dr. Lee had mentioned, and all clusters will have time in both arms of the trials, usually a control and then the intervention. And we randomize the sequence in which they transition from usual care to the intervention. So we see here our clusters of friends from before, and we would have them move over at different periods throughout. So in this example, our sequences, we have 5 of them. We had 1 cluster per sequence. In other settings, you can have multiple clusters per sequence. Other important features are the periods and those steps. So the time of the periods are important, as you need to ensure that you have enough time to for the length of steps indicated by the arrows. Now, this is a great design, but it does, because it reduces the efficiency. Sorry, it increases the efficiency relative to a traditional cluster randomization trial, but there are additional considerations. So for example, we've now added a new source of correlation based on the period effect. So there is a confounding by time that needs to be taken into account in our analysis. It's more complicated correlation structures and also has some more complicated analyses that need to be considered. We also need to think here, because we have repeated measures for clusters, we also need to consider whether or not the individuals within the clusters have repeated measures as well. So is this a cross-sectional cohort where each cluster period has a unique set of individuals, or is it a cohort design? So the same individuals in the cluster are also in the different periods. So we need to estimate the 2 correlation structures, and this would be the within period correlations denoted by the darker blue arrows, and the between period correlation, which would be the same cluster but across 2 correlations. So what do we do in terms of the analysis for this? Well, Hayes and Moulton has a textbook that has some general suggestions here based on the number of clusters. So often when we have fewer than 30, we would want to use a cluster level approach. This could be either non-parametric or a parametric approach. And then if we have more than 30 clusters overall, i.e. 15, we can move to an individual level method. So cluster level methods may be more robust and computationally simpler, but they do require two-stage approaches for adjusting for individual level covariates and may be less powerful. Individual level methods are more efficient, but they're likely to be sensitive to assumptions about the within period and between period correlations and could experience convergence issues when we have small samples. So what's typically done in practice? Despite these recommendations, individual level analyses are more frequently applied and generally easier. Another perk is that they naturally accommodate variable cluster sizes. So we decided to go with an individual level analysis. And when you do that, there's two broad approaches that we could use. You can have a marginal or conditional model. So the marginal or population average model, we typically think of a generalized estimating equation. And I really like in Eldridge and Carey's textbook, they provide a really good understanding of how that might impact your interpretation. So with a population average, we would think that if an individual in the population moves from the control to the intervention arm, what will the effect be on average? Now, if we think of a random effects model or a conditional model, this gives more of a cluster specific interpretation. And so here it would be if an individual stays in the same cluster, but that cluster moves from the control to the intervention, what will the effect be on average? Now, most of the time, we are often interested in what's going to happen for the individual. So we often think of marginal models as the ones that we're interested in. Okay, so when we're trying to decide, the selection of the model might be limited by the availability of data. So sometimes we only have data at the cluster level versus the individual level data. It might be based on how we want to interpret the results. It could have different methodological considerations. Again, bringing back that cohort versus cross-sectional. If we have the repeated measures, not just at the cluster level, but at the individual level, then we may need a hierarchical model. We also always need to think about the design of the study, how we randomized to ensure that that's reflected in our model. We've also discussed the variance inflation because these types of trials are riddled with correlation. But some other pieces that aren't often discussed are the variable cluster sizes. So this can impact your power when you have a variable cluster sizes. So you can think in this study, if we were looking at physician offices in an urban area, might be quite large compared to physician offices in a rural area. So this is another great paper by Eldridge et al. That talks a little bit about using the coefficient of variation of the cluster size and how it might impact your analysis and design. We also have those small samples because we only have 6 clusters here. And so there's a great paper by Merrick et al. That discusses cluster randomization trials with small numbers of clusters. All right, so when we're trying to decide the design, there's a lot of things that you need to think about in terms of the clinical, epidemiological, statistical, and practical considerations. And, we have to marry all of these into identifying the most appropriate model. George Box has the wonderful quote, "All models are wrong, but some are useful." I've already mentioned that we need to align the analysis with the design, including that method of randomization. And we also have potentially the availability of methods. So methods may not be available within the specific context to meet your needs. In this case, the register now had a binary outcome, and most of the work for stepped wedge designs have been in the continuous outcome field. So we had to extrapolate from those work for our binary outcomes, even though we don't really have a good understanding of how they would be applied to different outcomes. Alternatively, methods may be available, but there's a delay in their application. And we see this a lot with the small sample corrections. There's many methodological papers that speak to the need to adjust our cluster trials for small samples, particularly when you have a limited number of clusters. From a survey of the literature, most stepped wedge designs have fewer than 10 clusters. However, there is a delay in application as investigators and trialists become more aware of this. Another piece that might influence which approach you use, either for your small sample correction or your model, is whether or not your model actually converges. As mentioned in my earlier talk, most models are built based on the law of large numbers. So when we have small samples, things start to break down. Some other helpful considerations that we won't have time to get into right now are considerations for consent. And Dr. Garg had touched on this quite nicely, providing some references. There's also the Ottawa Statement on Ethical Design and Conduct of Cluster Randomization Trials. There's the risk of bias, particularly when we use cluster randomization trials for those individual level interventions. And of course, we always want to make sure that we're reporting accordingly. So the consort statement is used for trials, reporting of trials, and there are some extensions here for pragmatic trials and cluster randomizations. So finally, I'd like to end with some advice that I would give Spider-Man if they were designing a trial. With great trials comes great responsibility, and that's the responsibility to know advantages, limitations of your intervention design and data analysis. All right, so just have some references, but now we'll move over to Dr. Zwarenstein.
Hi, I'm going to describe some early randomized trials at ICES that I was involved in. These were proof of concept studies for the possibility of large ICES RCTs. Next slide, please. Thanks. Our most famous studies at ICES have detected the unexpected side effects of drugs, but others have evaluated the effectiveness of both clinical and policy interventions. And it's this last, the policy interventions, which is my main interest. Now, observational studies can't fully control for unknown confounders, and so are less useful for effectiveness research where the effects are small. Next slide, please. So when I started at ICES in 2002 and saw the comprehensive coverage, huge scale and low cost of ICES studies, and their external validity for Ontario's population, I wanted to try and use these data for some large pragmatic randomized trials on the effectiveness of interventions in order to achieve this double whammy of both internal and external validity. Next slide, please. There were three main barriers to the use of ICES data in randomized trials. Firstly was linkage. It's not possible to link individual data to the outcome or the intervention. Secondly, we needed an outcome which was accurately recorded on ICES data, which meant that any proof of concept trial needed to have a procedural or a prescribing process measure as its outcome, or mortality, something nice and clear. Thirdly, we needed control over allocation. In other words, the ability to ensure that the people we wanted to get an intervention got it. And for this meant that we needed to choose an intervention which was not central to decision makers' policy current interests at that time. At the time that provincial authorities and guideline groups were mailing kilograms of printed educational materials to family doctors every year. These were usually evidence-based guidelines, but there was no evidence on the effects of mailing these guidelines out. And so we had to do an ICES RCT because an observational study wouldn't work on account of the fact that every practitioner is usually sent these printed educational materials, and so there's no one left to compare with. But even if we could find an observational comparator group, confounding might hide a small real effect. And it wouldn't have been possible to test this using primary data collection, as it would be too expensive to do a large study. So we decided on a knowledge translation intervention and specifically printed educational materials as a proof of concept for ICES data systems as a platform for randomized trials in Ontario's real world context. Our trials were not trying to advance implementation science by testing a hypothesis or a theory of practice change, and nor were they trying to understand the mechanism of action of a knowledge translation intervention. The OPIM trials were what Schwartz-Verlusch would have called pragmatic trials. Their intention was to inform decision-making in a direct fashion rather than to advance scientific understanding of the underlying mechanism of action. Next slide, please. We received $300,000 of CIHR funding, which was enough to complete a program of 3 separate pragmatic randomized trials of printed educational materials. Next slide, please. We used the typical ICES inclusion and exclusion criteria. I won't get into them, they're on the slide. Next slide, please. And we did 3 separate randomized trials covering different targets. Each trial was independently re-randomized. And in each randomized trial, every eligible family physician practice in Ontario was included and randomized along with every eligible patient. So hence 3 cluster randomized trials. Using ICES systems for this study achieved a very high degree of external validity for Ontario because we randomized the entire study population. But even had we taken a representative sample of that study population, it would still have given us true statistical generalizability. And there was no point sampling when ICS data is so easy to obtain for everyone and the intervention risk is low. Now, generalizability is a more certain type of external validity than applicability. And it was generalizability that we were able to achieve to the specific Ontario population. In typical randomized trials, the notion of applicability is based on arguments for the similarity between what is usually a convenience sample in the study and the reference population from which it was plucked, usually only a few selected hospitals or jurisdictions. And their statistical relationship with the reference population is arbitrary. And therefore, for applicability of a typically conducted randomized controlled trial, sampling statistics don't apply accurately. Next slide, please. We tested 2 types of intervention against the control in a factorial trial. The control was an evidence-informed newsletter, which ICES produced at the time with a high readership among family physicians. For the trial, we sent a different edition of this newsletter to every family physician 3 times. Each time, it was a vehicle for 2 actual interventions that we were interested in. The one intervention was sent as an insert, folded into the newsletter in the same format as articles in the newsletter itself. That's shown above in the slide. And this narrative insert was on the topic targeted for behavior change in that randomized trial. Next slide, please. The other intervention was a short, succinct, and brightly colored postcard-sized item folded around the outside of the control newsletter. It was written in a punchy, directive style like that used by pharmaceutical company marketers. Next slide, please. The factorial randomization is shown above. The control group received informed only, another group received the long inserts, third group received the short one, and the fourth group received both. Next slide, please. I'll describe just one of the 3 trials, the retinal screening trial. The frequency of retinal screening had just been reduced for the general population. Reimbursement had been restricted to annual reimbursement for annual testing was restricted to people with diabetes only, but this was not widely understood and the awareness of it amongst physicians was low. And so there was a fear that retinal screening would drop. Since retinal screening was threatened, we developed an intervention to promote amongst physicians regular retinal screening. Identification of eligible participants at the physician level was done using the CPSO databases, which give the practitioner a number, and transcription of this list was automated, checked by hand, and then linked back into the database for randomization, generating of labels, and for analysis. We started with about 750,000 Ontarians with diabetes, and after applying our inclusion and exclusion criteria for patients and physicians, we're left with about half that. We linked these patients to about 4,000 practices with about 5,000 family physicians. Next slide, please. This slide, describes just the results of just one of the 3 trials. Neither the entire population randomized nor any subgroups of patients or of practitioners showed any effect of any of the 3 printed educational messages. This one showed for retinal screening, but the others were the same. These have very narrow confidence intervals and led us to conclude that when delivered by mail, single-shot printed educational messages in short and long formats alone and together showed a similar lack of effect. These internally valid, precise, and repeated findings of zero effect for printed educational materials aimed at a number of different interventions, a screening intervention, a drug initiation intervention, and a drug intensification intervention, should discourage any decision maker from hoping for practice change from mailing out printed educational materials. But how far this conclusion applies beyond Ontario and beyond similar interventions is of course not yet known. Now, using ICES systems for this study achieved the highest degree of external validity possible for Ontario by randomizing the entire study population. Several other trials at ICES have used different versions of this, some randomizing the entire population, some randomizing samples. This study, I think, showed that ICES data systems could support large pragmatic trials. Other trials that I did in which we were randomizing policy interventions such as clinical care pathways for home care showed that when the randomized trial is attempting to test an intervention in the real world, a policy intervention in the real world, decision makers are quite reluctant to let go of enough control over the timing and allocation of the distribution of their new intervention to permit randomization. And so I think what we've seen so far is that for clinical trials and for knowledge translation trials, it is possible to do them using ICES data systems. But policy trials are still an outstanding challenge for us to do trials using the ICES data systems. And that's not a problem with the systems themselves, it's with our relationships with decision makers. And so I'm hoping that Noah, who's going to talk now, will explain something about how to solve that problem. Thank you very much.
Hi, everyone. I've been given a tall task of solving a truly wicked problem in 2 minutes or less. I just want to say, the OPUM trial actually changed my life. Reading that protocol and ultimately Merrick became my PhD supervisor. I'm thinking about how we can leverage ICES to, as Amit said earlier, like actually not just see what the problems are in the health system, but try to do something about it, really has guided my career. And the other thing that was mentioned earlier, maybe about 20 minutes ago, when Doug mentioned JAK2's effect trial, the late and beloved JAK2, that also had a huge impact on my life. So a lot's been said already. I'll just sort of highlight a couple things, then we'll wrap up. Next slide. First of all, what I do is implementation science. And so I don't think about that much. When I'm a family doc, I think about what is the evidence for these things that I'm recommending or not recommending to patients. But what I like to do scientifically is try to understand, as it's described in this slide, what can we do to get family docs like me to do the evidence-based thing more often? Okay, so it's a level of abstractive away from, does this thing work or not? It's about behavior change, really. Next slide. So we have this great grant that lets us do a series of things in partnership with health system decision makers, trying to understand how we can change health professional behavior with amazing colleagues, and I don't have time to name them all. Next slide. And so these are a couple of our active implementation science trials going on right now. The first two that I'll talk about. Next slide. Because I don't have time to get into it in detail, we have published the protocol, and the first author there is this wonderful postdoc that's been working with me, Dr. Scholdener. So just shout out to her and other team members that might be with me today. And if you want to take a screenshot and Google that, then you can read about this neat linked trial. Next slide. this is the list of types of questions we hope to answer in this trial. And some of them are very mechanistic, and some of them are entirely pragmatic. And the neat thing is that it is possible to embed the one into the other. Next slide. So this shows diagrammatically these trials that we're running right now that entirely use ICES data. And so on the right, I want you to start on the right. We have about 4,000 odd family physicians who have signed up to receive reports from Ontario Health. How are they doing for their prescribing? So it's not these printed educational materials that Merrick was talking about, but actual data about their actual care. And in this case, we're particularly focusing in on antibiotic prescribing, which has actually changed quite a bit during the epidemic, not surprisingly. Now, what about all those docs that don't voluntarily sign up for reports from Ontario Health? Well, we have a partnership between Ontario Health, our research team, ICES, and Public Health Ontario to identify those docs and send them reports too, even though they didn't voluntarily sign up for it. So we have on the left side about 5,000 family docs that are being randomized to get one of 4 types of reports or no report at all, which is usual care for those docs. So one of the amazing things about doing trials at ICES is not only can you move towards trying to make a difference, but you can do it at massive scale, which is what Merrick was talking about. We basically have randomized every single family doc right now in the province to get information in various ways that aim to change their antibiotic prescribing. Next slide. Oh, yeah, perfect. So the basis for the intervention and the basis for analysis is all ICES data. So that's really the key here. Next. And I mentioned that we've embedded mechanistic stuff in here. So the idea is that we can do a whole bunch of surveys with these docs. And then I won't belabor this, but next slide. We can then work with, at length, the contracts departments of various organizations because we buy them cookies and treat them nicely and try to find ways to link data in novel ways. And so again, novel ways of that only doing a trial with ICES can enable at this kind of scale. But it does require lots of contracts and lots of data sharing agreements, and it's a bit of a pain, and you have to become friends with your contracts people. Next slide. The ethics stuff has already been commented on. I just want to highlight one thing is that when you're doing cluster trials, it's worth thinking really in depth about who is the research participant and who, therefore, you do or don't need consent from. And with ICES work, what you really want to do, next slide, is think critically about whether you can get a waiver of consent. And this was touched on earlier. I won't belabor it, but the TCPS2, the sort of Canadian version of that governs ethics, has something that lays this out, and there are a bunch of examples now of ICES trials where the terminology waiver of consent isn't quite proper, but basically we pursued effectively waiver of consent. And one of the things that comes up here that's very important is this research, big R, or is this some sort of program evaluation of a quality improvement initiative? And I don't have time to get into it. It's probably an hour-long talk on its own, but there's a lot to think about when considering where exactly on that spectrum this kind of work falls. Next slide. And so I just want to emphasize above all is that solving these sticky challenges requires partnership. And not only that, the reason we're doing these interventions is that we want to lead to some sustained change, some sustained behavior change, and some sustained policy change. And that requires partnership too. So if there's one thing I can leave people to take home, it's, think up front about all the partners that would need to be involved and get them on board at the beginning. Okay, that was quick, right?
Amazing job, Noah. Thank you so much. And thanks to all of our speakers today. It's been an incredible session. I really enjoyed it, and I'm just sorry that we didn't have a chance to field some questions from the audience. Those of you who do have questions, please feel free to write our panelists or me, and I can pass the questions on. But just thanks again to everyone who took part today. And we'll break now, and the plenary session will be starting in just a few minutes. So we'll give people an opportunity to have a break. But thanks again, and hope you enjoy the rest of the forum. Take care.